look after children. I'm Phil Howland, so this is me, and you are in the Introduction to Finite Element Methods. The sign on the door said music something, because it was still from session 1. So if you thought you were here for a music class, leave discreetly during the break. That's fine. So you've got me for the whole term, the whole session. There's only 7 or 8 weeks of formal lectures, and so we've put all the lecturing early on. The latter half of the course is devoted to project work, and we'll talk about that in a moment. So good morning. So what are we trying to learn? Finite element methods. Big, popular elective. Who has some sense of what they're going to learn over the course? You've seen finite element analysis before, just like a picture of it? No? Okay. Less than I thought. A little bit? Okay, good. It's good that it's a popular course. I think it's both something people are doing a lot professionally as engineers and will do more of, and we'll talk about why that is. So what will we learn over the course of 13 weeks? This is things that you will learn, and this is things that you'll demonstrate to me that you have learned, and that's how assessment works. So we want to apply the fundamental finite element analysis techniques to solve simple engineering problems. So we're going to do that by hand. We're going to define the mathematical, how does this work? These will mean more or less to you depending on how familiar you are with finite element analysis anyway, but we'll throw them up. So we're going to do some stuff by hand and show how FEA works even at the very fundamental level. And then we're going to move towards software solvers. And so in this course, we'll use answers heavily. And so how do they work? They're not magic. The results you get aren't perfect. So we need to understand what they're doing mathematically so we can know both the power and the limitations of the results they produce. We are going to then use software, FEA software, to solve problems. Some of those will be problems that we'll prescribe, and I'll introduce the guy sitting in the corner soon. Some of those will be problems that are prescribed to you. The group assignment's an example of that. For anyone who's been on Moodle so far and read the group assignment, that's something where we've said, solve this problem using the tools. It's still a little bit open-ended. There's multiple ways to do it. And certainly the major project at the end, which is a large feature of this course, is you choose a problem to solve using the software. So we'll try and guide it initially, like scaffold it, hey, do this sort of thing. And then certainly at the end, it's very open-ended. Solve a problem of your choice. And I think it's a feature of the course and a good one. And that kind of is point 4, perform a finite element analysis study to investigate a real-world engineering problem. And really, here, of your choice. So start thinking about that. Start thinking about things you're interested in and might be interested to do. Assessment, and then I'll introduce Jake and let him go, because I said I only keep you for 20 minutes. So how are we assessing you over the course of the session? You need a 50% out of 100 to pass the course. Anything more than that is obviously desirable. It's a 4th year course, so it's 4th year weighted if you're interested in WAMs as an undergraduate. So what are we doing? The first thing we do is a group assignment. So that's an engineering report worth 15%. Learning outcomes assessed. This is a table in your course outline. Points 1, 2, 3, and 4 relate to points 1, 2, 3, and 4 there, in case you're interested in what are we trying to demonstrate as we undertake this. So group assignment, points 1 and 3. And that's due Thursday of week 5. So it's week 1 now, and it's a group assignment. So we need to form a group, understand the assignment specifications, learn some theory, and how to use the software, because there's a software component as well. Perform some analysis and write a report and edit it together as a group and put it together in 4.5 weeks. Is that? Yeah. Okay, so we're going to start the session hard, but after that crash course, you should have a good understanding of the software, the method. You'll write a report. We'll get to mark that report and send it back to you, and we'll say, hey, at your next report, do this bit better. And that's going to help, right? Because you'll get this experience of writing a report together, and that will help in your major project report, which is worth a lot of then the assessment. So we'll try and hit that early, get some feedback to you, get you in the deep end, and then when it comes to the major report, you'll be a bit more familiar with what's required. There's 2 Moodle quizzes. There'll just be short quizzes available for 24 hours from 5 past midnight in the morning to 5 to midnight in the evening on these days. And they will quiz you on lecture material. So things that I present in lectures, the theory, there's some multiple choices, some calculation type questions served through Moodle. There is a practical exam in the final exam period. It's a 3-hour exam, which is unusual. Most exams have been pared down to 2 hours now. And the practical exam, what I'd like to do with that is, the scenario is, so you've just spent 13 weeks nominally studying FEA and learning how to use ANSYS as a piece of software. It's like your boss walks in at 2 p.m. and says, there's this problem, solve it before you go home today. What can you do in a short period of time? And the analysis is simple, not a big emphasis on report formatting or grammar or any of that sort of stuff. Just what logic do you apply and how good's your solution? So that's your short term, this is how things go. This practical exam and quizzes come out of, a year ago or a year and a half ago, the course had a 30% written exam. So you'd sit down and be presented with a problem and say, describe how you would use software to solve this problem. And so, you'd write by hand what you would do. So this is designed to be a little bit more authentic in terms of, okay, you've got this problem, now use the software to solve it. Don't write to me how you might solve it, demonstrate your competence in that area. So that's what that gives you. And then the major project, which as I said, very open-ended, solve almost a problem of your choice as far as it fits in the finite element analysis domain, 55%. And that is, what could you solve given, 8 or 9 weeks? I mean, you've got 13, but you don't know enough yet. You'll kind of start it in week 6. So given 7 or 8 weeks, what could you solve? So that's your longer term, broader demonstration of the software. So the expectation is you're using more advanced features, you're solving a more complex problem, and that's there. And that's given in a few different submission. There's a draft submission worth 20%, there's a major submission worth 35%. We might talk about that as we get closer to it, but be aware there is this large piece of assessment coming up. I've introduced me. Jake is the head demonstrator for the course. So do you want to talk about you?
Yeah, sure.
Good.
Hey guys, so I took FEA last year. I've done a lot of work in it. I'm doing my thesis in it. So any queries about the course, please email me. I can deal with most of them and I'll get back to you ASAP. Use the Moodle forums because a lot of the times questions will be repetitive. You might have the same question as someone else. But if it's not suitable for Moodle, feel free to email me anytime. Do my best to get back to you ASAP. I just wanted to reiterate what Phil said. Does anyone want to have a guess at what the most dangerous thing about FEA is? No right or wrong answer, but I've got my view.
Getting it wrong.
Yeah, related to that. Good. So FEA won't tell you when you set it up wrong. So as well as knowing how to use the software, you still need to have a background knowledge of, is what I'm putting into the software right? So as well as training you how to use the software, you still need to have a good fundamental engineering knowledge of, does this even make sense what I'm setting up? Because a lot of the times you can make a generated solution, but you have no idea whether it's going to be right. So hopefully that's something we can teach you throughout the semester. As well as that, I just want to briefly touch on the course outline. We've changed it a lot since last semester. So this year, this semester, we're introducing a presentation. That is not meant to be something that I want you to spend days and days preparing. All it is for you guys to sit down with your mentor and basically say, here's what I've got, this is what I've got to do. Because in the past, this draft submission was peer marked only, and what we found was that students were recognizing that if the mentor is not going to see it, I may not have to put in as much effort. So to kind of compensate for that, we took out an individual assignment, so we took out one assessment, and we want you guys to focus more on developing your major reports throughout the semester. So hopefully that gives you a bit more time. And the practical exam, it's not going to be hard if you know what you're doing. With most exams, I guess. But just think of like what we would test in the FEA exam. Things like symmetry, setting up your boundary conditions. I'm not going to ask you to define a whole composite layout or anything like that. But I'll talk more about that closer to the day. As for the group assignment, I'll talk more about that in the tutorial, but can everybody please do the group survey by Friday? So if you don't do it, I'm just going to randomly assign you. So please do that. It's on Moodle. It's going to close at midnight on Friday. It takes about 30 seconds.
Hang on, was that midnight or midday?
11:55 p.m.
Ah, drat. There's a pity that's not AM.
That's alright. So yeah, just do it. Just do it today. It'll take 30 seconds. And I'll get the groups created by the tutorial next week. I think that's all I wanted to touch on. Oh, my contact details are on Moodle. Please use the subject query that I put there. It just helps me sort my emails out. I think it's FEA query or something. So if you could do that, that'd be really good.
Good.
That's it.
Cheers.
Oh, and for the group assignment, I will release the template answers file, which will help you set up the boundary layout if any of you guys have had a look at the spec so far. And it'll help you define the parameters too. So I'll put that up either today or tomorrow. But I don't anticipate you guys will jump in too early anyway. It's only week 1.
Well done. All right, cheers. You're welcome to stay or go or do your thing. No worries. Cool. Sorry, I had misread. I thought it was 11:55 AM, which would have meant we could define groups Friday afternoon. If it's 11:55 PM.
It's 11:55 AM. I'll leave.
Yeah, can we re-advise? Because that's better. Because that way, going into the weekend, you'll know what your groups are and you can start making contact. I think that works.
Yeah. And just one thing as well, this year we're trying to introduce a few more lectures towards the end of the course. So we're going to have someone come in about week 9 to show you how to do a more advanced FEA simulation. We'll probably do 2 more lectures towards the end as well, one on major report writing. So how can you get a good mark in your major report, just some tips, probably by myself. And finally in week 13 I'll run through last semester's exam, show you how I would set it out, what kind of things we're looking for, because I found that last year a lot of people spent time on areas that weren't super critical and they could have maybe managed their time a bit more.
So basically you're running lectures on how to get marks in the major report and how to get marks in the final exam. Your lectures will be more popular than mine.
See about that.
Good. No, cheers. All right. Any other questions? So any questions about course administration? Because I think, yeah. All right. We've got a little bit of admin and then we start talking about content.
Oh, good, actually.
Yeah, no, go.
You probably see as well, a lot of the times on Moodle, I say the submissions are due at 5 p.m.
Yes.
That is just to encourage you to get your assignments in as early as possible. Most of the time they close at 11:55 p.m. and you'll be able to see that. So when you see it say 5 p.m, really there's no penalty up to 11:55. But if you email me at 11:40 and say something's not working or anything like that, generally it's much better if you email me at 4:30. That's what I'm saying. And just note, if something's not submitting and it's 11:50, don't just email me and say I tried to submit. Send me your file or the report as well, just so I have a record of it and timestamps. Just if there are any issues in the future. That's it.
No. So that's true. So yeah, we've got to watch a little bit. Some of the deadlines are hard deadlines. So like the draft submission deadline is a hard deadline because of the peer marking tool that we use. Some of the submissions are 5 p.m. for midnight. And so that a group assignment would be an example of that. So we'll talk about it. We'll do Moodle posts. Hopefully you won't be surprised by anything. Always ask a question if you need clarification. Excellent. Good, thank you. Cool. Just a little bit on the tools we're using for the course. Moodle, is it anyone's first session at UNSW this session? Maybe postgrad? Good. Little contingent. All right, no worries. So we use Moodle as our tool for getting around. Have you logged on yet? Yes, good. Okay. Okay. You'll get emails. Yeah. Okay. It's worth mentioning. Cool. It's worth mentioning that. Which keyboard do I need to use? This one's so. Oops. So I always Google UNSW Moodle. I search UNSW Moodle to get here. This is my page. I'm studying an introduction to university learning and teaching and convening advanced thermofluids and so forth, doing some other stuff. Where this course here, and I get to see stuff that's hidden, so my view's a little bit different, but we'll generally do announcements. You're all subscribed to announcements on your email. It gets pushed to you whether you like it or not. You can't unsubscribe. The other forums you can subscribe to or not. I would recommend reading the course outline. I'll tell you what's going on and all the assessment details. There's a little video from Dr. Garth Pierce and myself. We haven't written the exams yet. Down here in lecture topics, if you click on these, it takes you through to the other tool, worthy of note. Which is OneNote. Sorry, I've got it on my laptop. So in OneNote is, so for example, this week is FE Basics, all right? There is the PowerPoint that I'm using for my lecture and a printout of the sort of things that are on the PowerPoint. There is lots of other material and little discussion points that is more than we'll cover in class. I'm going to fill that out as the class goes on. And there's also your ANSYS work-throughs here. So this is what you'll be doing in your software labs on Tuesday afternoons. Okay? So OneNote's the place where all the files will go, and as the weeks progress, we'll put up more FE Basics, numerical solution procedure, the element library, and so forth. So that's all available for you there.
Just wanted to add as well, I had some issue accessing it with Safari, so if you're finding that when you click on it, it just blanks a page, you may have to either open it in the OneNote app on your computer or just use Chrome. I'm not sure why Safari is blocking mine, but
it's true. That's Moodle. OneNote, so we use OneNote extensively. When I will try not to write on the whiteboard, I'll try and write on my tablet, on my Surface, and that way it synchronizes through to OneNote, so you can access it there. And the software tool that we'll be using most is ANSYS. Again, so if you can search for UNSW My Access, and you can get the same version of ANSYS as we're using the software labs remotely. So from home or from on campus, but on your own device. So that's through UNSW My Access. There's a little install, and it sets up like a virtual desktop. And if you go to the ANSYS website, you can download a student license, which has a restricted number of nodes, and they'll give that to you for a year if you're a student. So if you've got a student email address, they'll give you a student license. And that's useful for smaller simulations, just getting a use for it. And that runs on your own machine, uses your own processor and RAM. Cool, good. That's it. Anything admin? Yes, go.
Are any of the lectures being recorded?
All the lectures are being recorded. Yeah.
Is it just the projector or is it you as well?
Good. That's what those guys are for. No, it's me as well.
Oh, okay.
Yeah. I'll take it as a compliment. Or maybe you're like, I'm less interested now. No, so the course has got, I think, 80 face-to-face students and 40-something web students. So you can get access to a live lecture. So there's a live lecture happening right now. And the recordings are also available afterwards. They're on Moodle under the live lecture link. Yeah, go.
Is there a way to download the OneNote so we don't have to go online and access it?
Is there a way to download the OneNote? If you go to office.com, yeah, good. No, yeah, you download the app. It synchronizes, and then it doesn't persistently download. It synchronizes and does the delta. It's a good question. Yeah. So I use OneNote on my desktop, obviously, because I use it a lot. Good. Good. So that's admin and tools. What's the time? That's not too bad. Half an hour of burning the first lecture on administrative stuff. Okay. What's finite element analysis? Let's do that. So this is like a high word, we'll spend a little while unpacking this, but this is like a wordy definition. I use FEA and FEM interchangeably. Arguably, the analysis is what you're doing, the method is the way that you're doing it. But we're trying to solve field problems using numerical methods. So what's a field problem? Is we're saying that some variable is changing or has some variable distribution in space. So what are some things that can vary through space? And this is you. So you get to do some talking now as well. So what are some things that we might be interested in that will have a spatial distribution? No. Yes, go.
Like the dimensions of a beam.
Yep, so the dimensions of something, so where, yep, how deflected something is, absolutely. Good. Might be interested in temperature. It might be hot here and cold there, right? So I've got a listed examples, that's okay. I'll give you another opportunity. Rightio, have a look at this. I think it's funny, if a little inappropriate. What's funny is I can see the people who aren't getting to the end of the joke because they're still working on the problem. Nerds don't. So here's the question. And it's just a funny little, it's not mechanical, sorry about that, it's electrical. But the question is, what's the resistance between those two nodes? This is a really difficult problem analytically. I've seen the solution and I got no idea. Numerically, setting up a grid of about 100 by 100 resistors and putting the two things there, you get within a few % of the analytical solution. And you could do this trivially if you've got a reasonable understanding of FEA. With resistors, so I don't do enough electronics to know, but resistors, they come in tolerance bands. What's the gold tolerance band stand for? Because there's like red, brown, silver, gold. Yes, no. No one does yes. Do you know what it stands for though?
Not off the top of my head.
It's like 1%. It's like a 1% or 2% thing, right?
I think silver's 1 gold's 2, but I'm not.
Good, excellent, that's fine. So it's in the 1 to 2% range, right? So here, the resistance against a numerical solution, so numerical is where you're just using numbers and a calculation that's rough, but close enough, right? So the resistance against that would be, but it's not ideal. The real solution involves pi. I don't know why. I've seen the solution and I can't tell that. The numerical solution obviously doesn't, it just comes out as a number, right? But you can get a numerical solution that's more accurate than what you can actually physically build because of the tolerancing on these components. And for engineers, that's often enough. I had someone who was doing numerical simulations of diesel combustion as part of their research here at the school. And they were telling me a story and they said, because we've got an experimental arm, people who are taking photos and videos of diesel as it combusts. And then we've got a numerical simulation arm, people who are simulating what might happen as diesel combusts. And he was in the simulation arm and he was saying to me, we're getting better results in simulation than the guys are getting in their practical labs. Like we're better representing what happens in reality than the people who are taking experimental results and looking at reality. Like, yeah, that's not how it works, but sure. All right, good. So we're looking at field problems. That was voltage. Voltage isn't even up here. So the thing that varies through space is voltage. So the different nodes have a different level of voltage, for example, and you can track that, and then based on volts, you can know amps if they've all got 1 ohm resistance, and so you can solve that problem. I think it's a bit of a fun problem to solve. Other things we might be interested in. Temperature is a property that might vary spatially. Stress is something we'll talk a lot about. So we'll largely look at things from a stress basis, but there are other things. Magnetic flux densities here, voltage we've just mentioned, concentration in a porous medium of something flowing through the medium. So there are other things that we can care about that we might want to numerically simulate. Like I said, not all, but we're talking in the region of when the analytical solution is hard. Okay? that we introduce numerical methods. And for example, can I draw with this? Sorry, I've had to go to a different computer. So for example, on this problem, the analytical solution works great, and it's perfect, and it's wonderful. Great. It doesn't work if this resistor out here is changed from 1 ohm to 2 ohm, like changing the value of a single resistor that's almost inconsequential, breaks the analytical solution, totally. Numerically, doesn't change, like the complexity of the problem isn't changed at all if each of these has a different value. So numerical solutions are a lot less sensitive to small changes and less ideal situations than analytical solutions. So we're getting towards what FEA is. And I know I'm using analytical and numerical, and you're like, we haven't defined those words yet, but we're kind of, hopefully we're working towards an understanding. So where can we use FEA in practice? Then I've got some nice pictures to kind of give some context. So we can use FEA as a simulation tool, for example. So we've got a structure, and we want to know how that structure behaves. ANSYS, the guys who publish ANSYS at the moment, are pushing, because they're developing and so forth, they're pushing a concept called the digital twin. So you'll have a real device, say a crane hook, some sort of, or some lifting device, something real, a structure, a bridge that trains are going across. They've actually digitally twinned the area around the Sydney Opera House. And if you're interested in, say, stress or temperature or something that's happening on a component that's really difficult to measure, right? So say the critical component in a crane is some component that you can't reach with a strain gauge, right? But you could strain gauge up the outer structure, because that's easy, and then you could simulate, okay, based on these strains I'm seeing on the outer structure, this must be happening to my inner critical component, okay? So you're simulating the response of, and potentially the whole structure, just based on a few measurements and digitally twinning. At the Sydney Opera House, they're looking at wind loadings and wind chill factor on human comfort. So they take wind measurements in 1 or 2 locations, and then they know based on that how the wind is flowing throughout the whole thing. And if you put displays or obstructions or whatever, you can very quickly simulate then what will happen. So that's a thing ANSYS is pushing. Then the question must be, okay, well, if we can simulate, well, at what point will those loads, at what point will the structure, at what point will a scenario be considered to have failed? And so we can test that with a reasonable accuracy if our model is good. And that's definitely something we would care about as an engineer. A lot cheaper to do in software than it is in reality, testing things to failure. And or we might be designing from scratch or modifying an existing structure to improve its function. So you've done a simulation, you've found a critical corner where the stress is the highest. Okay, if we add a radius to that, if we cross brace using a different thing, how will that change the stresses? Will I create a new stress concentration somewhere else? So this is the difference between reactively something keeps failing at a corner, let's brace that corner up. Well, maybe it starts failing over there now. Okay, let's simulate the whole thing and hopefully design out those sorts of problems. So this is why we might be using FEA. So let's talk about structural analysis. Why would we use this? Can I build it? Because I don't know how this looks from the back. That's a stamped, cold-drawn component. So you start off with a flat piece of metal and you stamp it, and then it ends up in some sort of shape. That's really tough to do analytically. Like to think if you start with an end shape in mind, the question is, because you know that things have elasticity, so you're going to stamp it and it's going to spring back a little bit, right? What shape does your die have to be for you to achieve some end shape such as you desire it? That's a really tough problem to solve. ANSYS, among others, has a particular module to do that, and they're customizing that. A flip phone, is it durable? No. But anyway, one could simulate and so forth. So areas where simulation are more valuable or can start being valuable rather than prototyping. You don't want to build a whole production run of cars before you have a sense of whether you're putting the crash, the crumple zones in the right place, the airbags in the right place. You'd like to do that in a software scenario, get it reasonable, then build a prototype, crash a few prototypes. Yeah, a lot of these are airline related kind of things. Cool. Hopefully this is a problem that you could trivially solve. It's like first year mechanics. And this is how we introduce mechanics to first year students. We say, well, let's idealize our structure and make it full of trusses and make some assumptions about moments not going through the nodes and so forth. That's a first year problem. This is a second year problem, I think, for us. Right? Hoop stress and longitudinal stresses in a pressure vessel. The problem in practice with this pressure vessel is you can't put anything into it or get anything out of it, right? And so you'll always have an opening, and that's a hassle to deal with. There was a news article 3 or 4 weeks ago from what major airline carrier is considering building planes without windows. There's a question. What major airline carrier, international, is considering building planes without windows because it'll let them make the planes lighter because they won't have to have holes in their fuselage? Did anyone see that news article?
Qantas, was it?
It wasn't Qantas, but they're allied with Etihad. They reckon they can put cameras on the outside of the fuselage and project onto something that looks like a window, something that looks enough like you're looking outside, because to be in a plane would be freaky, right? If you couldn't look outside, they reckon they can simulate what it looks like to look outside enough that passengers will fly in it. If they can lighten off the plane and make the air tickets cheaper. They're looking at it, right? Holes in a pressure, because a plane is a pressure vessel. You're flying in a vacuum, you pressurise the cabin so everyone has enough air to breathe. Holes in a pressure vessel are a real problem. Or, this is our truss example. So as soon as you put in a redundant member, so we've added one member here, not a problem, it becomes a different class of problem. You go from statically determinate to statically indeterminate, and I talked to David Kellerman. He thought his students, this is our second year mechanics lecturer, he thought his students would be able to do that, but it's certainly a different class of problem. Whereas in FEA, they're the same class of problem. And nothing is ever this simple. It's not complex, but it's not even that simple in reality. Okay, that would be a much more representative pressure vessel you would manufacture. And this is a frame for car. Good, it's our Formula SAE Redback Racing car. And so now we've got multiple redundancies, and it's definitely not statically determinate. Okay, so allow this as a pressure vessel designed to AS 1200. I can't draw. Let me just whip up a draw. Turn that on. Excellent. Good. So, because I think this is worth knowing. So how does the Australian standards deal with, so there's your pressure vessel. Okay, so you've got a pipe going into the pressure vessel. So this is AS 4041 pressure piping and AS 1200 pressure vessels. So you do your maths as if the pressure vessel had no hole in it, okay, and it's got some thickness of the skin. You cut a hole in it in order to put a port there. All right, so there's your port, and it's going to bolt onto some pipe that's going to go somewhere. All right. Basically, what the Australian standard says, well, so you cut that much cross-sectional area out of it, so you have to add at least that much area there and there. So the area you remove must be the area that you put back in. And I'll put some welds there. That's called a compensation plate. And they're pretty common to see. I would say this is a low pressure vessel because I can't see any compensation plates around those ports. There is some compensation around the leg. That method is a conservative method. You end up with a heavier structure than you started with. The promise of FEA is, if you analyse the structure well, would you need that much compensation? I don't know, right? But you could analyse it, and you could lighten off your structure, you could reduce the cost of your manufacturing process, and potentially still comply with the standard because they allow for that sort of thing. Is simulation required? I would say you could get away with not, but you would. You would simulate. Cars, you want them to be light because mass affects acceleration, okay? Large industrial pieces, you want to reduce your cost of manufacture, potentially reduce the weight of transport, and so forth. So how do we simulate? Now it's starting to get, oh look, it's a pretty picture. I said pretty picture. If you had any awareness of FEA before now, you might have been thinking something like this. Typically it's a coloured diagram representing a 3D rendering of the object. There's bits that are red must mean bad. There's bits that are blue means good, that kind of thing. That's pretty typical of somebody's, and that's fine, it's not a wrong interpretation, but this is what people think of when they think of FEA. And what we've done here is we've taken this framework as part of the chassis, and we've broken it down into, you can see the little black lines, small discrete chunks. And the basics of the idea is, well, I don't know how the whole structure responds to an imposed load, but I could know how this little piece here is going to respond to an imposed load. Okay, so I can define that little cylinder of material. It looks cylindrical to me. I can define that little cylinder of material to say, well, if I impose some forces on that end and then impose some forces on that end, static equilibrium must be maintained. The forces have to cancel out. And then if I could do that and define some equations to say what that state will be, and if I could do that for every little chunk, and then impose my loads on some pieces and supports on other pieces, then I could solve that all at the same time in one ridiculously large simultaneous equation. That's actually what we do. And that would tell me what each piece is doing structurally. And that turns out to be the finite element method. You define discrete elements, small pieces, that you can define and say, well, I know what's going to happen within this small piece, and it's connected to these other small pieces. And then we solve them all simultaneously, and so that every little piece has its defining equation satisfied, and then voila, the whole piece comes out. How small should the pieces be? How large can they be before they start to degrade the quality of your solution? If we were trying to approximate pi by putting straight lines around a piece, we could start with 3, 4, 5, 6, 7, 8, 9, 10 straight lines, and the perimeter, right, so the sum of the length of the lines, would start quite off what you would hope it to be and get quite close to where you'd like it to go, the more pieces you put in. So so this is analogous to FEA. The more pieces you put in, the closer you get to the analytical solution, the more computationally expensive it becomes. So the more processing time it takes, and you have to define how close to the line do you know, and or if you don't know where the line is, so say you didn't know what pi was, at what point do you say, okay, well this line's starting to look horizontal, let's stop there, and that's what we'll actually do with our FEA method. We'll analyse the structure, make the pieces a little bit smaller, analyse it again. The stress has changed. Has it changed by much? Is it changed small enough that I can say I've analysed the structure? And so that's a decision we'll make as we go through. How are we done? Oh no! I looked at the clock as if it was something 30. Did anyone notice me looking at the clock earlier and say, we went okay, and anyone thought he doesn't know how to read an analog clock? Did you see it though? And no one told me. Ah. No, that's the clock I'm looking at to tell me the time. All right. I'm like, time seems to be dragging on. 11, 10. Okay, good. We're going 40 minutes. I like to take a break at the nominal hour point. So we'll talk a little bit about this and then we'll take a break. All right. We need to establish a more trusting relationship. If I say something stupid or you see me do something stupid, you'd kindly let me know. There's a kind way to do it though. Cool. So what's FEA? So how's it come about? The mathematical formulation started in the 40s. So this is like pre-computer or certainly pre-personal computer. Large corporations having some computing resource. Freeware becomes available in the 60s. I love that. So this is people just playing around, saying, what are we going to do? How can we simulate reality using these mathematical principles? In 65, some companies said, oh, that might be useful for us. And so you know that they've started to see the value in it. Nastran and ANSYS are both big packages today. So they started, well, that became 50 years ago. They've been working on their software. NASA, of course, cares about simulation because it builds space-going craft. So that one wasn't a hard question. Westinghouse, of course, cares about simulation because it builds. No, it does, but no. What's not? So that's how I feel. Like I'm an Australian. I'm like, I don't know what Westinghouse builds. Any of the international students know what Westinghouse does? Yeah?
Gas turbines?
Gas turbines, nuclear power stations. Wow. Yeah, I know, right? It's like, no one told me. No, so they were doing nuclear power stations in the 60s, and so cared about simulation because space travel and the nuclear industry are bits where it's better to do simulation than experimentation on how things go wrong, for example, right? ANSYS is what the course used to be software agnostic, so like you could simulate using whatever software you like. And it's really tough to administer. But if you wanted to learn COMSOL or Nastran, you'd be most welcome to use that in your major project, for example. If you presented a good project, well simulated, it's just really tough to support when there's multiple platforms. So we've kind of settled on ANSYS, and that's what we'll be supporting, I'll be talking about. But certainly this is meant to be FEA, and the mathematical formulation and some techniques on good and bad FEA practice apply across the board. Right, so I will talk about ANSYS, but it's certainly, there's a couple of big ones. 96, they spun out as their own company, so no longer part of Westinghouse. And a couple of years ago, they were worth $14 billion. So this is big, big business. What's the most expensive piece of software you can conceptualize? How expensive do you think you could make software and people would still buy it? $400,000? It's not that much.
Wow.
But no, it's order of magnitude. It's somewhere between $100,000 and $200,000, depending on the modules you buy. So if you, as a private industry, buying an ANSYS license, that's what you're paying. So we didn't use ANSYS at the Steelworks where I worked. We used Strand 7 because it's a cheaper package. Probably, but it will become cheaper and good solutions will roll out more. ANSYS is certainly at the peak of what you can spend on a package. So they were, so they're worth a lot of money. Some other things are going on. So modules coming in like material modules, a dynamic module. So the idea that we're not just interested in things when they're still, but we're interested in things when they're moving. Comes out start of the 90s. And I don't know what software looks like in the 60s because I wasn't around. But I know what software looked like in the 80s because I was around. And it wasn't what it looks like now, right? Like you're probably doing a lot of programming, a lot of text interface kind of stuff. You're probably reading numbers as an output, not getting graphics. So there's a lot more of draw something up in SolidWorks and then import it into ANSYS. You know, back and forth between things. Certainly, you know, draw something up you're happy with and then send it off to be manufactured, 3D printing and machining and so forth. What are we using it for? Well, there's some things. Basically, anything you can define the mathematical relationships of how something small relates to the things next to it, you can develop a FEA module for. You could understand it as being able to be solved numerically. And this is us. Like I said, I came around, you know, I've been around since about then. We're around there. So the basic idea is that processing power will, there we are, double every 1.5 to 2 years. Computers getting more powerful. The computers are now, they're powerful enough that the power of computers isn't what's stopping us from solving problems, right? It's what we do with it, it's how we put the theory into them. And as Jake was saying, you can do something and it looks great and the solution is totally wrong. And that will be the limiting factor of how well, particularly, you know, in the limited context of your major project, for example, that will be what limits you in doing well in your major project, not the software or the hardware. And in terms of going forward with engineering, yeah, hardware is no longer our problem. Let's take a break there, because then we're going to actually hit some of the element types. I like to take a break. Let's come back when the minute hand is pointing at the 6. No. I make it 8 minutes too, so let's come back at 11 o'clock neat. And I'll start getting, sorry, that's very intro-y, but we'll start talking about FEA and some theory. It'll become very mathematical very quickly. And everyone will go, oh, now I'm comfortable. Oh, thank goodness. Okay, cool guys, have a break. Hello. Yep, good, excellent. Excellent. Cool, all right. Let's call that a break. Hopefully you feel refreshed. I don't sit down when I'm on break. I like to stand and stretch and do physical things. But that's just me. I certainly encourage it. Cool. So we're going to talk a little bit more in detail about finite element analysis. We're trying to define it. We're trying to lend ourselves towards formulating some FEA. And then towards the end of the hour, and I don't know, I don't think we've got an hour left. We might, early knock. But towards the end of the hour, we'll do some one-dimensional simplified analysis just to show a way that these things can be framed up. So that's our thought. So we're talking about finite element analysis. So finite, right? Finite means not really big, and it means not infinitesimally small. Okay, so finite means they have some size that can be measured and thought of and talked about. So what's some examples of how we could put these things together? So if your structure is long in one dimension and small in the other two dimensions, okay, then we might be talking about a one-dimensional element, and we could use the word bar and beam. Now they're different. We can explain why they're different. And when I say long in one dimension and short in the other two dimensions, what I mean is the properties change in one dimension, but the properties don't change significantly in the other two dimensions. And you can achieve that by having things that are small in those dimensions. But you could have something that's long in two dimensions, okay, but the force is applied evenly across the whole thing. And you say, well, I can simulate that as being a one-dimensional object because it's replicated throughout the thickness. So we're talking about things where the properties change along one dimension, so bars and beams. Then you have objects that are large in two dimensions and small in the other dimension, which is to say you don't care about the property variation across the thickness of the object. Okay, and you can think of those as being two-dimensional objects, and we can say that those are plates and shells. Again, there's a difference between plate and shell, but we'll get there. And then you have objects that are thick, or the properties vary in all three dimensions, and we call them bricks. Okay. What's this, the structure in the top left? It is the Harbour Bridge specifically, right? Situated right next to house, at which these are present. No. Anyone? Less trivial and obvious. It's not an anchor. No, but it kind of has that hook structure. It's part of an artificial knee. So that goes on the end of the femur, and the tibia will hook into it. No, but it looks a bit like that, right? So you got a bone stick up to it, right? But you can kind of, they're just pictures, right? Harbour Bridge wasn't built using FEA. But you could see the thought that you'll have a thin structure, making up a shell, and you'll have, the properties will vary through the thickness of this object. So you need a brick. So it's about what information do you need as an output? What's the physical geometry look like, and what information do you need as an output? We'll talk structurally, so we'll talk stress and strain a lot. The other variables analogously can be done the same. Actually, temperature is easier in some ways than stress and strain. Some words that we're using. Okay, so node. So everywhere that two lines come together, right? We're going to call that a node. You can also have mid-side nodes. So you can have nodes along the side, but let's just keep it nodes at the corners. Right, elements is your chunk. I should just make a comment on bricks. This brick has 6 faces. It kind of looks like a cube. We call that hexahedral. 6 faces, hexahedral. Okay. It's also a brick if it's any other 3-dimensional shape. And tetrahedral is the other big 3D shape we like to work with. So a shape with 4 faces. Okay, if you played Dungeons and Dragons as a kid, you know what a tetrahedral shape looks like. I feel like I'm going to hit about 50% of the room with that. You know, engineers more so than other populations you would get with that analogy. So it's a brick, even if it doesn't look like a brick, if it's not a rectangular prism. So elements, so the volumes of material between the nodes. Mesh is the word that we use just to describe the breaking up of a continuum body into discrete chunks. And you could have a fine mesh being small. You could have a coarse mesh or large mesh being large elements. So large elements, small elements. You start to talk about that. You talk about your meshing or your mesh. Okay. Loads, typically forces, pressures, self-weight. So the weight of an object is a load. Within FEA, loads are only applied at nodes. So that might not be obvious, but if you apply a pressure, for example, that would be reasonable. You know, the crankshaft's applying some pressure, so this inner sleeve. You apply a pressure to that surface, and that resolves out to be forces at each of the corner nodes. So loads are only applied at nodes, and boundary conditions are this node can't go in this direction. So it's either fixed, so this node can't move at all, or maybe it's against a surface, so it can only move in this two-dimensional plane. That would be considered a boundary condition. And again, boundary conditions are applied to nodes. And material properties. What's the material properties that we might care about?
Fatigue.
Sorry? Fatigue? Not a material property. Oh, no, you're thinking way too advanced. Young's modulus. Hardness, yes. Fracture toughness, I think that's too advanced again, but yes. So it's okay. So you guys are thinking failure criteria. Who said fracture toughness? You? Yep. You guys are thinking failure criteria. Let's get there later. Absolutely. So Young's modulus is the driving thing that we care about first of all. Later on, we bring in density if we're talking about something dynamic or self-weight.
Does geometry come under material property, or is that more about the actual material?
No, so material property is independent of geometry. Absolutely, yep. So how does this material behave? Which is really good, because you can determine material properties in a standardized testing environment with a cylindrical bar under ASTM standards, and then you can use that material to make a complex geometry out of and generalize the material properties. It's quite a power and a strength of the method. Cool, good. All right. Yeah, so when I say you can get almost any field variable across a spatial distribution, what things need to be true of that variable, and one is compatibility. So when we come together as nodes, so this is considered a compatible mesh, this one is not compatible, right? So the nodes and the edges have to be compatible from one element to another element. That makes it really hard to, for example, use some 1D elements and then merge them in with a brick. So you've got some bars, and then you merge them in with a brick. That interface is really complex mathematically because it's hard to get compatibility. So often within one model, you'll see the same type of thing. You can do it. You can't trust the results at that interface. You can do it, but we won't deal with the maths of that. So compatibility, they fit together. Equilibrium. So at every node, so I've just talked about what a node is. So on the nodal corners, okay, the forces will sum to zero. And if something's moving, if something's dynamic, we pretend like they sum to zero by allowing the acceleration, the inertia to provide a force, and that kind of keeps us in equilibrium. We'll do dynamic analysis in week, I think it's 8, maybe 7, so it's quite a late topic. So just talking about static equilibrium, that is applied at the nodes, okay? And we need some sort of law to define our primary and secondary properties. So primary property is how much for structural analysis is how much do things move. E here represents our material property, which is independent of geometry. and stress is probably the thing we care about. Will it break? We can do some of our thoughts about analysing that. So we need some sort of law that defines or relates what we're going to find, which is nodal displacements, and what we care about, which is stress. I think that's the simplest example, and I think it's the one that we're most familiar with. We'll see how complicated this gets in a few slides' time. So stress, we're just going to talk a lot about it. I'll recap it quickly. That's fine. So we're talking about a pressure over an area. So for simple 1D bar, okay, you've got a force P, sorry, force divided by area is stress. If you were to take that down to the smallest element, then you can say, you know, it's a limit case as you make the area infinitesimally small of how much force does that much area take, okay? And this is a good example of that because you'll actually get stress concentrations near the hole. So any formulation that we put together would need to show, for example, more stress closer there than it shows on the outside. Sorry?
Did you call about the projector being off?
I didn't.
Oh.
Did someone call about the projector being off? Because I've deliberately turned that projector off.
Okay, cool. No.
Fascinating.
No worries.
No, good. Drop by any time. There's a network problem, but I'll catch you offline. Thanks very much. Where was I? Cool. We can also apply the same, in this case in shear, so we've put some hollow cylinder in torsion. Sorry, I have turned this projector off because I like to stand not here. Now's a great, no. Yeah, I'd like to be more like this, and I don't like a projector in my eyes. So we can apply the same thought concept in shear, obviously a hollow cylindrical body, we've sheared it up. We can apply the same thought in a general case, okay? So no one's analysing this, but it's just a thought of, if you take a cut through a body, then each small element of that body, of that surface, is experiencing some normal force and some shear force in some direction. And we can think of those in terms of axial and shear stresses. All right. As we find, you're all mechanical, well, not everyone in the room is a mechanical engineer. You don't have to be a mechanical engineer as postgrad, but I'm assuming some mechanics knowledge. So this should be familiar, although it's complex. Okay, so you've learnt it before, although it is complex. And so we can set up some sort of cube of material, and we say it's got some axial stress and some shear stress in a few dimensions. Comfortable? I'm comfortable, good, excellent. All right, and so we've got our shears, those are meant to be sigmas and taus. Sorry, the font isn't rendering correctly. And so we talk about stress being a tensor. And we say that each infinitesimally small point can have a different stress. Right? So it's something that changes spatially, which is good. Oh, that's dreadful. So this renders right on my laptop. I'm blaming it. That is potentially going to be a problem. Let's duck across to my laptop, if I've still got it open. Rendered right on my laptop in my office. Is that really not going to set a V? Cool. All right, let's ignore that for now. Good, that's working. So basically what it's saying is, yes.
What does tensor mean?
No. Here's my problem with that. My problem with that is, right, so people who, undergrad, do you undergrad here with David Kellerman? Do you do 2400 with David Kellerman? Okay, the problem I have is there's an academic at the school who that is his bag. And I've had students, there's students in the room who have learnt mechanics with him. And anything I say would totally be like, people in the class could call me out on it based on my understanding of it. And a very defined understanding of it isn't required to do FEA analysis. Briscoe, I'm looking at you as someone in the room who could call me out on But you could look it up. So that's really unsatisfying. And I don't like to lecture stuff I don't know. But where we get to is, sorry, so whatever, this is rendered as an image, that's fine. Where we get to is what we, am I on my laptop now? No. That's annoying. What we wanted was stress equals Young's modulus times, so this is our stress term. Okay, so this is analogous to, we've got a stress term, we've got a Young's modulus term, and then we've got a strain term, so which is how much the material is deflected. Okay, so our stress term comes down to stress in the x direction, stress in the y direction, and stress in the z direction. So axial stresses on our little element that did render. And then shear stresses on our x surface, on our y surface, and on our z surface respectively. Okay, so by knowing the values of these stresses, we can start to think about, will it fatigue, will it fail, those sorts of things. So this is what we want to know. Our E term, if you're just dealing in one dimension, Young's modulus can just be an E, and that's fine. As soon as you're dealing with a three-dimensional element, E itself becomes a large matrix. You're not memorizing this matrix, but it's the maths that's happening in the background. We'll take this up to 2 dimensions. So this is a three-dimensional case. We'll make the matrix a little bit smaller. But you could, and then this is then our strain. So extension in the x direction, extension in the y direction, and extension in the z direction, and then shear on the x face, y face, and z face respectively. Right? And so how this sort of thing works is, say a body only strained, so strain means movement, like an extension, okay? Say a body only strained in the x direction. You'd want to say, well, it's going to have stress in the x direction and no other stresses. And the stress will just be Young's modulus times the strain, right? Not the case, because we know that as a body strains in the x direction, as it's stressed in the x direction, it strains in the x direction, it's going to want to compress in the y and compress in the z. So if it doesn't do those things, if it only has strain in the x direction and all these other things are 0, for example, then its stress in the x direction is actually a little bit higher than it would otherwise need to be, and it has stress in the y and z direction. I'm really suffering from not being able to draw on the screen, so sorry to those on the recording. I'm just going to flip across to my laptop. There we go. So what we're saying is, so this is our analogy. So we're trying to relate stresses and strains, and we're using a Young's modulus-like analogy to do so. So what I'm saying is, say you knew the value of strain x, and all these other ones were zeros. 0, 0, 0, 0, 0. Cool, excellent. Based on how matrix multiplication works, epsilon x is multiplied by everything in that column, and then everything else is multiplied by zeros, so you can disregard all these bits of the matrix. Okay? And so what we find is, and our question is, what's our stress based on that? So our stress in the x won't just be Young's modulus times the strain that we see in the x, but indeed, how much stress we see in the x will depend on the propensity of the material to reduce in the directions in which it's not stressed. So we bring in Poisson's ratio, here shown as nu, and indeed, you will get some stress in the y direction. So the stress in the y direction will be this constant times by this ratio, and you'll get some stress in the z direction, which will have the same value. And that's kind of how this is put together. Right? So this is saying that you don't just get stresses in the direction that's strained, you also get stresses in the other directions because of the effect of Poisson's ratio. Poisson's ratio, reasonable range of Poisson's ratio for a metal? 3.3. Oh, did you say 3.3? I said 0.3. 0.3? Excellent, good. Good. I thought you said 2.3, and so I put a 0 in front of it because I was like, yeah, let me help him out. 0.3 is a good value, right? So 0.28 to 0.33 would be a reasonable kind of range. Elastomers and rubbers, are they higher or lower? Higher, right? Natural rubber, you can start getting close to 0.5, and that causes a problem here. Because 1 minus 2 times 0.5 causes a problem. So, let's ignore that and carry on. No, elastomers are a tough material to simulate. I've got a thesis student working on it at the moment, which is kind of fun. But, so this is for general case. Let's focus on what's generally true. So you don't have to remember that, but it's how it's formulated and it's how this kind of stuff works. If you did matrix maths we do it in first year or second year here? First year. If you did matrix maths in first year and then you haven't touched it since, now's a great time to brush on your matrix maths. It's just a good excuse. Studying FEA, I'll do some stuff. YouTube channel 3 Blue 1 Brown. Do a lot of matrix maths. Yeah, they do a lot of just great stuff. You should just watch all their videos anyway. But they do a lot of matrix maths as a primer and as an intro. Very visual. So, yeah, say I'm doing FEA, I'll take the time to work out what matrices are all about. Excellent. So we're going to be a little bit strategic about what we study. This is just the kind of elements that we've already talked about, but I've just displayed them a little bit differently to try and show the difference between bars and beams, for example. So these arrows represent the x, the y, and the z vector, if you like, for bars, and the double arrows represent rotation around that vector. Okay? So if we talk about bars, trusses, or indeed plane strain and plane stress objects, so this is a quadrilateral, you can do triangles in that, or bricks, it's true of all bricks, we can only have what's called degrees of freedom, or the ability to move in the x, y, and z direction. If we talk about beams as a 1D element, or shells, you need plates and shells, then they can also have rotation around the nodes. So we can track rotation and not just displacement. So these can be powerful in their appropriate applications. Some people say, well, we've just got bricks, so let's use bricks all the time. As we go through, we'll learn that's not. A, it's very computationally expensive, and B, the results may not be as accurate as a well-defined shell, for example. Yeah?
There's no 3D element with the moments?
There's no 3D element with the moments. Yep, that's true. So there's no analogy for that here because you need a dimension to rotate into. So the bricks and the shells, so that's defined on a plane, and when you rotate it, it rotates out of plane. Bricks don't have a dimension to rotate into in the reality that we care about as engineers. But it's a good point. No, it's a good point. So yeah, go.
What do the U, V, and W represent?
Yes, my apologies. X, Y, and Z direction.
Oh, right, okay.
No, great question. Like, why do you know that? No, sorry. And theta's obviously, of course. Sorry, rotation around the same axes. Thank you. If you get into it, we use a lot of letters of the alphabet because you're trying to define all that stuff. And you'll see this in the example. If we get to the example, how am I doing time? Oh, fixed a clock. 13 years as a maintenance engineer. Know how to fix a clock. Radio. Bars and beams. We have a problem with letters. There's not enough letters in the alphabet. It kind of gets fun. So bars and beams. So here's an example of a structure that has long, slender members. All right, lends itself well to one-dimensional elements. Okay, let's not use computational power of bricks. And over here, we are doing it's called a modal analysis. So the question is, at what frequencies will the structure vibrate fundamentally, given its nature, and what will that vibration look like, mode shape, okay? And the lowest, we care about low frequencies here. Typically, the lowest frequency is 0.366 hertz, for example, and it will shake like that, at about 0.5 hertz. Okay, 0.42 hertz, it'll start to shake laterally, all right? About 0.5 hertz, it picks up an inner node and so forth. So we do modal analysis in FEA. Modal, it's looking at modes. The final exam last session, so just like a month ago, I asked students to do a modal analysis under exam conditions. Not of the structure that's complicated, but it's a reasonable thing we should know how to do. These are put together in strand 7. That's one of the packages available. What do plates and shells look like? These are just other solvers that aren't ANSYS. So where structures are thin or you don't care about the variation of, particularly in this case, stress throughout the thickness. So this is made up of thin plates of metal. This is an aeroplane structure. So it's got some reinforcing members through it. It would be appropriate to use shells through that. I'd argue some of these should be solid bodies, but I haven't seen the simulation or the setup. And bricks, when things have got thickness in all 3 dimensions and the properties change in all 3 dimensions within that element. So there's some examples. What can we get out of it? Stress strain. Yes, reaction forces, often important deflection, important residual deformation. You're plastically deforming something and seeing where it will spring back to. So residual. Buckling is something that we might care about and often overtakes stress or considerations in thin sections. Fatigue life, vibration modes, as I said, and loads in other bodies. So they're the sorts of things we get. There's lots of other things you can get as well, but they're the sorts of things we might be primarily interested in. You can't, the temptation is, was that a hand? No. The temptation is to just look at something, particularly if you've got a 3D model, like a lot of stuff is being designed now in CAD. So you're like, I've already got a model in SolidWorks. I'll just throw that into ANSYS and put 2mm by 2mm by 2mm bricks everywhere, press the solve button, right? It's not the best way to solve your structure. We do need to idealize, to simplify. Where do you care about? Where's your critical piece? You know, a structure like that, it's far too complicated for what we do. And that lends itself to then the part of the engineer. If you say, well, software, everyone can use software. My nephew and niece can use software, right? So where's the engineer's intelligence? The engineer's intelligence is, well, you've got something that's real, either exists or you're going to build it. How do you idealize that down to produce something that's going to be analyzed? And then discretization, how small will you make it? What elements will you use? And then the software, thankfully, does the maths, but you need to do the decision making. And it's a subject that lends itself to lots of different solutions for the same problem. Because a different engineer with a different opinion, experiences, whatever, could have a different model, different discretization. If they were both making reasonable assumptions, the solutions would be close to it themselves, would be fairly close. But there can be more than one right answer to that. We talked about mesh. You want to refine your mesh, so mesh, small mesh equals computational power required. You want to refine your mesh around places where your stress changes a lot. So in this case, small mesh around the chamfer, which is good. Large mesh away in regions that we don't particularly care about or the properties aren't changing dramatically. So that would be a well-refined mesh in those terms. And we use mesh refinement to bring ourselves closer to solving the mathematical model. If your real structure and mathematical model are tenuously linked, then you could have an example where you're like, I can't believe the structure fell down. My model's fine, right? Reality beat you. So what sort of things can we do? We'll flip through these. So this is ANSYS, strange enough. So we said you'd want to see stress concentrations around a hole and at fillets and chamfers, and you do. It accurately simulates those things. Contact is something that we'll look at as well. So you'd want to do contact loads and also internal stresses. This is really tough to do numerically because you've got 2 gear teeth in contact, and defining those so they're actually in contact is quite difficult. But anyway, that's fine. This is Professor Mark Hoffman. over in the States, and they're doing simulations on foldable satellites and structures. So you want something that's light and you want something that can be compact, and then when you get in space, it doesn't need to be strong necessarily, it just needs to expand out and unfold. And so this is talking about solar panels and different structures and how they can fold into a package for transport. That's a vertebrae. Oh, there you go. I didn't know that. Anyway, she's teaching one of my other courses. Dynamic analysis is showing a car crash. I won't go there because I want to do some maths. That's what we're here for. Stresses, as you can see, the stresses around the connection. So you don't want a refined mesh over here because what matters is, right, the connections in the worlds. That would not be unusual. What can we use? There's lots of software. We'll be focusing on ANSYS. Cool, excellent. Maths. Everyone's favourite part. Rightio. So let's do the bar element. So we've mapped out a whole bunch of elements. We're going to do the simplest element in the simplest way and solve a simple problem, right? And it's just getting you thinking about how FEA works. So let's talk about a bar. It has length in one dimension, and it's thin in the other two dimensions, or we don't care about how the properties change across those dimensions. And we might think of the bar as being like a spring. Okay, so it's got a node at each end. U, thank you, relates some displacement in the x direction. Okay, and we've got forces. We can only apply forces at the nodes. If you want to apply a force in the middle, you put another node in the middle, right? So that's how that works. It has some length, it has some Young's modulus, and it has some area. So we've got Young's modulus, an area, and a length. We've got forces. Forces here are mentioned as P. Forces can be P or F is fine. And the question is, what's the stiffness K? And how does it relate to the nodal displacements? And what we're going to end up with is this equation in the top right-hand corner. We're going to have some K value, right? So K represents our stiffness, relating our U values, which are our displacement values, to our force values P. Okay? And I'm going to do that in one node. Awesome. Actually, I can probably just go there. Nope. Nope. What do I call it? Element stiffness matrix. Excellent. Good. So we can apply this too. So there's lots of different bars here, right? If these are all one-dimensional bars, then there's only a few things we care about. Okay? So you say, oh, there's lots of different sections. When we bend them, they're going to respond differently. When we torque them, they're going to respond differently. When we're talking about these as being one-dimensional bars, the only thing we care about is the Young's modulus E. So they all have some Young's modulus E. And they also have some cross-sectional area A. If we're torquing or bending and we're interested in the response, we can't use bars anymore. We have to use beams. Yeah, basically, for a 1D with that, it's a beam. So we can model it down to this structure here. And so we'll give these nodes numbers, 1 and 2. So at either end of the length, there is a nodal number. Okay? And at each node, we have some displacement, U1, and some force P. Displacement U2, and force P2. Okay? Now, because this is coming up in one note, you've all got a copy of this. So you can write it down if you think that's helpful. You don't have to write it down if you don't want to. And so then the question is, how does P relate to U? And it's through this stiffness matrix, K. And so what are the values of K11, K12, K21, and K22? So the question is, what are the values of those 4 Ks? which are unknown. So what we can do is we come down, and if we displace U2 by a value of 1, and this works in whatever unit system you're working with, millimetres, metres, we often work in newtons, millimetres, and MPa in this subject, so let's displace it by 1 millimetre, okay? And the question is, what stresses then occur? So are we happy with whatever matrix knowledge you've got to say this equation means K11U1 plus K12U2 equals P1 and K21U1 plus K22U2 equals P2. So this matrix equation is a set of simultaneous equations that I've just described on the right. So if we fix U1 at 0 displacement and we move U2 by displacement of 1, then what does that do to our equations? Well, U1 is 0, so this goes to 0 and this goes to 0. So we end up saying K11 times 0 plus K12 times U2 is 1. 1 equals P1, and K21 times 0 plus K22 times 1 equals P2. So then, from this one, K12 will equal whatever P1 is, and K22 will equal whatever P2 is. And that's kind of nice. And we can know what P1 and P2 are, so they're our reaction forces, right? Or they're the forces required to create that extension, right? And I remembered from high school, you get E equals Flee. Good, that's like a first year mechanics kind of thing, right? So we've set our extension to be equal to 1 down here, so that's nice. That's equal to 1. And so the question is, what's the force, which is Flee, or you can say Pli, if you like. So E equals Pli. So make P the subject of that equation. From that you get P equals EA on L. And so that's true here, so P1 equals EA on L, and P2 equals EA on L, equals EA on L, EA on L. Except that this equation here, which we've dragged from our first year mechanics knowledge, right, implies that you know the direction of the force, and in fact, to extend that out by one of your forces is going that way and the other force is going that way, which isn't accounted for in our current maths. So, K22. So that actually needs to be a negative, and so we find that's a negative EA and L. And so we've defined now K12, wrong, my apologies. Sorry, it's the one on the left node that's pointing to the left. So that's a negative. So define K12 and we've defined K22, but we don't know yet K11 or K21. And so we can do that, find the value for those two K values by doing the opposite thing. So now we hold the right-hand node still, and we move the left-hand node by a displacement of 1. And then we get K11 times 1 plus K12 times 0 equals P1, and K21 times 1 plus K22 times 0 equals P2. And again, we know P1 and P2 because of the direct formulation for stuff we know in first year mechanics. And so we come out with, from this, we get K12 equals negative EA on L, and we get K22 equals EA on L. And so our final formulation of our stiffness matrix is EA on L, EA on L, negative EA on L, negative EA on L, times by displacements U1 and U2 equals P1 and P2. Sometimes written as EA on L, 1, 1, negative 1, negative 1, U1, U2. So the matrix is commutative, so we can bring the EA and L out the front of the equation. That seems like an unnecessarily complicated way of solving the stress on a 1D bar. Excellent. So what we've done, sorry I'm looking over the left screen, what we've done is we've defined our two positions of the nodes, we pull on one of the nodes and we say what happens to the reaction forces, and then, like the great news is if you develop some structure and make it out of lots and lots of these little 1D bars, then you know how each 1D bar behaves and you can solve the whole structure. Okay, so this is leading towards, that's basically the same words I said when we had the SAE redback framing up, right? So we define what each little bit does, and then we can solve the whole bit. That's on the OneNote now, so in all of my messy writing glory. So generally we'll find something like this, and it's true of bars, beams, bricks. So this scales up quite well. So we find P equals KU is our normal way of developing things. And it's almost trivial at this case, but it gets a lot more complicated and bigger. So what if we have multiple elements or multiple loads? So we wanted to apply a load in the middle. Well, like I said, you break it in two, put a node there, and then we've got now nodes A, B, and C. And we can have, elements A, B, and C, I've got to watch my language. Elements A, B, and C, nodes 1, 2, 3, and 4. It takes 4 nodes to define 3 elements. And those can have both forces and displacements to them. And now the question is, well, we know what an elemental matrix, stiffness matrix, looks like for a bar, but what would it look like for an assemblage of bars? And we break these things up. So we say that each bar has you're not a mouse. Point with my finger. That working? Yeah, cool. Let's do this. So each bar has a node 1 for that bar, right? So A has a node 1 and node 2. Then B has a node 1 and node 2. And C has a node 1 and node 2. Okay, and those all kind of come together and they say, well, displacement capital A here must be whatever the displacement of node 1 for element A is, because that's the only element that's touching that bar. And displacement B here, capital B, must be whatever the displacement of node 2 of A, right? But it also must be the displacement of whatever node 1 was for element B. Okay, so we've got some compatibility happening here where we're joining the nodes together, and it says, well, it must be true there and it must be true there. And node capital D over here only interacts with element C. Sorry, the letters are complicated. And so how does that work at node 1? Okay, so node capital A, apologies, node 1. Well, that's our stiffness, AE on L, times UA minus, so what's the forces that are happening at the leftmost node, PA, is our A on L for element A times the displacement of element A minus the displacement of element B. So it's how much that E, that extension value is, right, times by the stiffness, which we've defined as A on L. That's what the force is going to be. Now the force at node 2, some of that force is going to come from this element, and some of that force is going to come from this element. So it's the sum of those two forces is your overall force on node B, and that can be defined down here as being something related to the displacement of node A, capital A, something related to the displacement of node capital B, and something related to the displacement of node capital C. Okay, so we're kind of setting up our equations. We're saying when we join these bars together, we can define a set of simultaneous equations, and here they are, for force on A, force on B, force on C, and force on D, respectively. Okay? This top line of the equation, this very top line is just A on L of element A minus A on element A, sorry, A on L of element A times UA and UB respectively equals PA. So this top line here is, my apologies, is this equation here. And this equation here relating to element B, sorry, force PB, is this line here. So I've just converted a set of simultaneous equations into matrix form. And you can see that some of the A on L's, some of the stiffness, is coming from the blue element A. It's been boxed in blue. Some of the numbers in the matrix are coming from the green element, and some are coming from the purple element. So they've been boxed respectively. And so that's called an assembled or global stiffness matrix. So an elemental stiffness matrix for a bar is just a little 2 by 2, A on L, 1, 1, minus 1, minus 1. And we can assemble those together, and they form this kind of matrix. And so in general, I don't know what the R's are there for. That's meant to be an overbar, but that's fine. So in general, we get a global stiffness matrix times by our displacement vector equals our force vector. And that's a general case for all FEAs. So we break the structure down into small pieces. We determine the equation for each piece, and we've done that for a 1D bar. We set a global stiffness matrix together. If any of the nodes are known to be fixed, we can remove those out, solve for unknown displacements, and then we can get secondary quantities like forces and stresses and so forth. Let's do this exercise. Oh, we've got 10 minutes. We'll be fine. So this is for you. I'll do it too. Yeah, I want you to do something. I want to try something. Try and solve this. So, if you've got elements A, B, C, D, and E, and we've got a force occurring through through weight on masses M, 2m, and 3m, this is a one-dimensional problem. So even though there's some displacement off there, it's all considered the only motions are in one dimension. We've given some K values on the springs. And the question is, what would the displacement of all the nodes be? Is that right? What would the displacement of the nodes be? And then what would the reaction force against the top and bottom surface be? I'll No idea where to start? Going okay. Hello. Am I there? So basically what you're trying to do is set up a series of equations where you relate forces P to stiffnesses K times displacements U. And you've got 5 potential U's and 5 potential K's. U is the vertical displacement in this case. Yeah. Then having assembled those, sorry, my apologies, we are going to run out of time. So I'll just show you the run through. So you define stiffness matrices for Ka, Kb, Kc and so forth. Your force vector, which is mg times 1, 2 and 3 respectively, because it's 1m, 2m and 3m. Your u vector, well, you know what u1 and u5 are going to be, because they're 0 and 0. You assemble a stiffness matrix. So Ka joins u1 and u2, Kb joins u2 and u3, Kc joins u3 and u4, Kd joins u3 and u5, and these are E's, not C's. Right? E joins 4 and 5. Okay, so that's an assemblage of a global stiffness matrix. And once we have an assembled K, sorry for running out of time. Once you've got an assembled K, we know that F equals Ku, because that's our definition, that's how we're going to work. If we take the inverse of K and left multiply by both sides, then we find the inverse of K times K is the identity matrix, and so you're only left with a U vector on this side. And we find that the displacements U will be equal to the inverse of K times your forces, which are known, Right, so that's a known vector. This is our unknown, is how much the things displace. And our K is what we assembled using the matrix above, using the assembled global matrix above. And then we can solve that for U and get our various displacements. So on the one note, this is a description of discretizing the structure, assembling the global matrix, cancelling things out, and solving for U and so forth. So that the solution is there. I wanted you to think about it for a few moments without that guidance. Excellent. There's no software labs in week 1, so the next time I see you will be this time slot next Monday. Thanks for coming along. I'm around for the next little bit if you want to ask any questions. Thank you very much.